Thermal power plants represent one of the largest uses of water globally. The water usage in thermal power plants is described by two separate terms: water withdrawal and water consumption. Water withdrawal is defined as the amount of water removed from a water body for introducing into the power plant, while water consumption refers to the portion of water removed, that is, water lost in the system by evaporation, and it is unavailable to other users. Water requirements in the thermal power plant mainly includes: for using is boiler feed water, for running the steam turbine, for circulating in the cooling system, for ash cleaning, and for desulfurization of coal-fired plants. The main demand for water within a thermal power plant is for its cooling system. Dear friends, welcome to our YouTube channel, Tech In Out. This channel produces videos on various topics of engineering and technology. In today's video, we will present a technical talk on water withdrawal and water consumption for cooling water system in thermal power plants. The power plants, which use fossil fuels, biomass and nuclear material for electricity generation, are called thermal power plants. The energy conversion process in thermal power plants involves converting the chemical energy to thermal energy, which is then converted into electrical energy via mechanical energy. Thermal energy is produced by the combustion of coal, natural gas, petroleum liquid fuels, biomass, and by the reaction of nuclear material for obtaining steam. The steam so produced is used in driving the turbine. The turbine drives the electricity generator, which converts mechanical energy of the turbine into electrical energy. The steam exhausts from thermal power plants continue to be the most common source of electricity, and currently they account for 80% of global electricity generation. Coal is the dominating fuel source used in thermal power plants. For electricity generation, nearly 50% of the thermal power plants in the world use coal as the fuel for getting thermal energy. South Africa uses coal for 94% of its electricity requirement, while China and India use coal for 70 to 75% of their electricity needs. However, to achieve international climate goals, the world will need to shut down nearly 3,000 coal-fired power plants before 2030. If it is to have a chance of keeping temperature rises within 1.5 degrees Celsius. Cooling systems are the most water-intensive part of the thermal power plants. Cooling water is withdrawn from a water body such as river, canal, lake, or groundwater wells. This water is circulated in the cooling system to condense the steam. The circulating water takes up the heat of the exhausted steam and itself becomes hot. This hot water coming out from the cooling system is discharged back into the water body. There are three types of cooling systems: once through cooling system, recirculating, or wet cooling system, and dry cooling system. Some power plants use two or more cooling systems together. These cooling systems are called hybrid cooling systems. The options of fresh water resource for thermal power plants include surface water and groundwater. The fresh water can be costly to source in the large volumes needed by thermal power plants. In hot and dry summers, the supply of fresh water requirement for thermal power plants can become a bottleneck. Thermal power plants with fresh water cooling systems are more exposed to fluctuations in water availability, as their water needs are considerably high. Regulatory restraints by governments may impose limits on increase the cost of fresh water usage by power plants. Significant areas of almost every country face a high level of fresh water stress, including large areas in China, India, South Africa, and the USA. Historically, almost all early thermal power plants used once-through cooling system. The once-through cooling system takes a large amount of water from the water body. The cooling water goes through condenser of the cooling system for condensing the steam exiting from the turbine. The hot cooling water is then discharged to the water body. The discharging cooling water temperature is slightly higher than that of the withdrawn water. Since once-through system returns water to the water body at a higher temperature, carries risk of entrainment of aquatic organisms. Power plants utilizing once-through cooling system also are subject to increased incidences of shutdowns or curtailments during times of drought and extreme heat. Recirculating cooling system is also known as wet cooling system. This cooling system routes the water through the plant's condenser and then recirculate the water within its cooling system. The cooling water is kept circulating in the system, absorbing the heat from the steam. The cooling is chiefly achieved through evaporation, with simple heat transfer to the air. The amount of heat that can be rejected from the water to the air is directly related to the relative humidity of the air. Air with a lower relative humidity has a greater ability to absorb water through evaporation, simply because there is less water in the air. Evaporation of water is the major source of water loss in this cooling system. This cooling system withdraws much less water than once-through cooling system. Sometimes an on-site pond or canal may be sufficient for the plant's cooling water requirements. Dry cooling system uses air instead of water as the cooling medium. This system sends high-flow forced air through fin tubes in the condenser within which the steam circulates, and the air transfers the steam's heat to the ambient air directly. Heat is thus transferred to air by means of a process which is less efficient than wet cooling system. When ambient temperatures reach about 40 to 45 degrees Celsius, the cooling capacity of these condensers gets derated. One major advantage of dry cooling system is that by eliminating the need for cooling water, it offers a much greater flexibility of plant location, as it does not depend on a major water body. Hybrid cooling system, a fourth cooling option, combines the elements of water cooling and air cooling systems. This cooling system, consisting of wet and dry sections, utilizes the benefits of both dry and wet cooling systems. Hybrid cooling system helps balanced water withdrawal and energy savings across a variety of weather conditions. This system is typically designed to be operated as dry cooling systems during the cold seasons and supplemented with wet cooling during the hot seasons when dry systems lose their efficiency. Hybrid cooling systems can consume low volumes of water for much of the year by operating primarily in dry mode, with the flexibility to operate more efficiently in wet mode during the hottest times of the year. In general, selection of a cooling system for thermal power plants depends primarily upon following factors. Number 1. Plant technology. That is, fossil fuel based, biomass based, or nuclear material based. Number 2. Plant size. Number 3. Water availability. Number 4. Amount of water requirement. Number 5. Available water resource type, that is, fresh water or non-fresh water. And number 6. Environmental concerns. The type of cooling system employed in thermal power plants is invariably the greatest determinant of water usage, in terms of both water withdrawal and water consumption. Water consumption rate is defined as water consumed in gallons or cubic meter for generation of 1 kilowatt hour or 1 megawatt hour of electricity. In terms of installed capacity and water consumed per megawatt hour of electricity generated, coal-fired plants are the biggest consumers of water among thermal power plants. In India, water consumption regulations mandated that thermal power plants set up before January 1, 2017 should not use more than 3.5 cubic meters per megawatt hour of water of electricity generated, and those built after the date cannot exceed 3 cubic meters per megawatt hour. The type of cooling system employed in thermal power plants is invariably the greatest determinant of water usage, in terms of both water withdrawal and water consumption. Water consumption rate is defined as water consumed in gallons or cubic meter for generation of 1 kilowatt hour or 1 megawatt hour of electricity. In terms of installed capacity and water consumed per megawatt hour of electricity generated, coal-fired plants are the biggest consumers of water among thermal power plants. In India, water consumption regulations mandated that thermal power plants set up before January 1, 2017, should not use more than 3.5 cubic meters per megawatt hour of water of electricity generated, and those built after the date cannot exceed 3 cubic meters per megawatt hour. Thermal pollution is the degradation of quality of water body by any process that changes its ambient temperature. The warm water heat, that is, released into the rivers, lakes, canals and sea by power plants can be classified as a form of pollution. Over a long operational period, thermal power plant cooling water can have a large impact on the water resource. The elevated temperatures of return flows alter the local physical and chemical properties of the water resource. The discharged warm water can harm aquatic organisms, affecting the whole aquatic ecosystems, that can kill a huge number of fish species. When power plants tap groundwater for cooling, that can deplete aquifers critical for meeting many different needs. Water scarcity is a challenge for the power sector in many countries. Regions where water is scarce face obvious risks, but even regions with ample water resources can experience constraints due to droughts, heat waves, seasonal variations, and other factors. Thermal power plants in areas lacking ample water supplies are vulnerable to power disruptions from drought and increased competition amongst water users. China, as the world's largest consumer of power, is also experiencing very serious water scarcity, while climate change will worsen water availability. The quality of water can affect the efficiency of the cooling system operation. Water quality typically varies based on seasonal factors, such as summer, winter, rains and droughts. The intended water resource needs to be evaluated regularly to ensure its quality. Water quality covers its characteristics and contents such as conductivity, pH, TDS, dissolved oxygen, and sodium ion concentration. The impurities affecting water quality can include turbidity, oil and grease, harmful microorganisms, heavy metals, nutrients, organics and dissolved inorganics. Moreover, the impurities can cause potential operational problems in the cooling water system, which include corrosion, scaling, fouling and biological growth. Appropriate water treatment can provide the required water quality for reliability, safety, efficiency, and economic performance. Water treatments should be capable of lowering the mineral content, such as calcium, magnesium, alkalinity, phosphate, silica, and removing suspended material. The pretreatment of raw water consists of biofouling control, typically by chlorination, and removal of suspended solids. A suitable chemical treatment program is determined according to the withdrawn water qualities and operating conditions, such as cycles of concentration and water temperature. For proper operation, the cooling water system needs a continuous dosing of chemicals to prevent corrosion, scaling, and fouling within the cooling circuit. The monitoring is an integral part of water treatment systems. Water treatment monitoring systems include manual monitoring, continuous online monitoring, and other monitoring techniques by employing automatic instrumentation. More than one techniques may be necessary to monitor a particular treatment system. Some of the value-added benefits obtained through proper monitoring of a water treatment are as follows. Number 1. Reduced risks associated with chemical underfeed or overfeed. Number 2. Continuing compliance with environmental regulations. Number 3. Improved quality of plant operation. Number 4. Increased water and energy savings. Number 5. Improved plant productivity. Blowdown is a term used in cooling water system, a part of water that is removed from the system, to reduce contaminant buildup in the cooling tower. The water evaporating from the cooling tower leads to an increasing concentration of impurities in the remaining cooling water. Cooling towers can cycle water numerous times before the water becomes saturated and it is discharged out of the system. To maintain chemical and contaminant concentrations at an acceptable level, a portion of the water is periodically removed from the cooling water system through a process called blowdown. The water is either discharged to the water body or recycled to the recovery system. The blowdown water is replaced with fresh water called makeup water. The water lost during the circulation in cooling water system is compensated by supplying makeup water. The makeup water dilutes the remaining cooling water in the system, and thus it brings down the overall concentration in the cooling water. The amount of makeup water required depends on the concentration of chemical constituents that need to be tolerated in the cooling water. The chemistry of the makeup water, including the amount of dissolved minerals, can vary widely. Makeup water obtained from lakes, canals, or rivers cause formation of biological fouling. When this water obtained from cooling towers can cycle water numerous times before the water becomes saturated and it is discharged from the system. It represents the accumulation of dissolved minerals in the recirculating cooling water system. Cycles of concentration for cooling water system is ratio of dissolved solids in cooling water and the dissolved solids in the makeup water. Cycles of concentration specify how often makeup water added into the system before the water has to remove as blowdown from the cooling tower. The higher the ratio, the more the impurities in the makeup water is being concentrated in the cooling water system. As levels of dissolved minerals elevate with higher cycles of concentration, scaling, and corrosion probabilities also increase. Traditional water treatment technologies offer the thermal power plant to operate at cycles of concentration at values of 3 to 5, depending upon makeup water quality and chemical treatment process. As the cycles of concentration increase, the water may not be able to hold the minerals in solution. To maintain cycles of concentration above 5, strict monitoring of water treatment critical parameters is required. Increasing cycles of concentration save water, because it essentially means that water is being recirculated longer through the system before being discharged as blowdown. From a practical point of view, the Different strategies are proposed to increase the cycles of concentration for thermal power plants to reduce the water requirement. Highly treated recycled water may be an effective means of reducing cooling tower consumption of makeup water. The high concentration rate would require higher quality treatment of makeup water. Cycles of concentration in a cooling tower are also controlled by adjusting the amount of blowdown water. The geographical location of power plants has a considerable impact on the type of cooling system options, water availability, type of water resource, and environmental impact. If any thermal power plant needs to be located inland, the availability of cooling water is a key factor in the location. Where resources of cooling water are limited, the importance of high thermal efficiency is great. Even if water is so limited that it cannot be used for cooling, then the plant can be moved away from the load demand to a location where there is sufficient water for efficient cooling, accepting line losses and extra cost for power transmission. Thermal power plants are sensitive to predicted climate changes, which will cause variations in temperature and precipitation, including the following. Higher mean air temperature will also increase the mean temperature of water used for cooling. Increases in water temperature are likely to reduce generation efficiency, especially where water availability is under stress. Increases in air temperature will reduce generation efficiency. Changes in precipitation patterns will reduce the volume of surface water and increase the temperature of cooling water. These trends may lead to operation at reduced capacity, and even the temporary shutdown of power plants. Adaptation measures can be enlarged or retrofitted cooling systems, including air cooling where water is expected to be increasingly scarce. In order to meet the cooling water demands for thermal power plants in a limited water availability location, alternative water sources are considered. Adopting alternative water sources for thermal power plants can help alleviate the impact of future water scarcities. Alternative water sources include treated sewage, high salinity water, seawater, brackish groundwater, water from mining operations, and produced water from oil and gas fields. These alternative water sources are available, each with different benefits and costs. The availability and cost of alternative sources of water can vary by location, but they are often comparatively cheaper, and they are readily available. Each alternative resource will cost more than traditional water sources, with the costs of treating the water and transporting it to the power plant site. Treated sewage effluent has been the most attractive source because of its year-round availability, inexpensive price, relatively low cost of treatment, and minimal impacts to operation. Seawater can provide an unlimited supply for coastal power plants. Desalination is required to supply their fresh water needs. Brackish groundwater and even brackish surface water are important resource for power plants in water-scarce regions. Mine water from abandoned and active mines could be an important source for nearby power plants in some regions. Produced water from oil and gas wells could become a significant source for nearby power plants, especially if oil and gas development continues. Water conservation in thermal power plants is becoming more important, as fresh water getting scarcer, and regional regulations on water use are becoming more stringent. Owing to water scarcity and limited water resources, there has been increasing global demand for reducing freshwater consumption. Fortunately, there is a range of opportunities and technologies available to conserve water within a power plants that includes following approaches. Number 1. By increasing cycles of concentration. Number 2. By decreasing amount of blowdown. Number 3. By introducing modified water treatment program. Number 4. By substituting one's through cooling system with wet cooling, dry cooling or hybrid cooling system. And number 5. By adopting alternative water resources. Globally, based on fresh water shortage situation, regulatory directives have been issued in number of countries to reduce use of fresh water by thermal power plants. Some of these directives are as follows. In 2017, in the United States, a number of power plants were forced to shut down or reduce power generation due to low water flows or high water temperature. In 2016, lack of sufficient water resources in South Africa have forced all new power plants to shift to dry cooling systems. In 2016, India amended the power tariff policy, requiring thermal power plants within 50 kilometers of a sewage treatment plant to use treated sewage water. In 2007, Australia had to reduce electricity production of its 3 coal-fired power plants to protect municipal water supplies. Thank you very much for watching this video. We deliver training courses on various topics of asset integrity management, corrosion control, and process safety management as in-house, public seminars, and online programs. As we battle the harsh impact of recent pandemic, we need your support even more, so that we can continue to offer you more quality videos. Our subscription portfolio has seen an encouraging response from many of you who have subscribed to our channel. More subscriptions to our channel can help us achieve the goals of offering you even better and more relevant videos. Your support through more subscriptions and sharing our videos among your circles can help us practice knowledge dissemination to which we are committed.